Okay, this is sig number 15, which is implicit differentiation, as you can see. The idea is we're trying to take the derivative, but there are some x's and y's all mixed together. And so we need to remember how to do that. So the first thing we're going to do is we're going to go ahead and write that we are going to take the derivative. And this particular problem is asking us to find the equation of a tangent line. So I guess I should have done this first, but the equation of a tangent line can look like this, right? Where we are already given x1 and y1 here, and then there's a slope right here, which the slope is going to be found by finding y prime, or in this case dy dx, right? Because this is the change in y over the change in x, which is by definition slope, right? So here we go, taking the derivative of this. The derivative of 4x with respect to x is just 4, technically dx dx, but because the variables match there, we don't need that tail. Then over here, when I take the derivative of this next piece, we need to recognize that these are two things being multiplied, right? So I'm gonna like break these into two pieces, call this one u and call this one v, and then use product rule on it. So the derivative of 3x squared with respect to x is 6x, and then we have to times that by v, so times y cubed, plus, right, so far we've done u prime v, plus we got to do v prime u, right? So v prime here is going to be the derivative of y to the third, which would be 3y squared, dy dx, because that's not in terms of y, right? Or that's not, the y doesn't match the x. And then we have to multiply that by u, which is u's over here, which is going to be 3x squared, right? So just write this, the u is here, right? V prime times u. And then we get to the right hand side, the derivative of 4y is 4 dy dx, right? So now that we've done that, our goal is to get all the dy dx terms on one side and everything else on the other side. Okay, so you know, there's a lot of options here, but for this particular example, it's going to be easier to move this over here just because it's one thing. Otherwise, I have to move all these other things over, and I have to move this the 4y dy dx to the other side as well. So I'm just going to move this whole term. The way I would do that is by subtracting, and so if I do that, I would get those guys there, and then we'd get on the right hand side 4 dy dx minus 3y squared. I'm going to go ahead and write this in a slightly different order, right? All I'm doing is rearranging that term that I'm moving and just putting the 3x squared in front of the dy dx, just so it's easier to see where those are. And so now we can factor out the dy dx, right? So here's dy dx. What's left on the inside is 4 minus 3y squared times 3x squared, which I probably should have cleaned that up a little while ago, but please notice that when I multiply 3 times 3, we're going to get 9. So let's go and just write that here. Let's go and erase this, and we're going to write 9. Right? 3 times 3 is 9. And now that this is factored out, I can divide both sides by this big chunk over here. So we're going to get 4 plus 6xy squared over 4 minus 9y squared x squared, and this is dy dx, right? So this tells me the slope, right? This is the slope equation. I need to know the slope at this point up here, right? 2, -1. So basically it means I plug in 2 for x and -1 for y, right? So a little notational thing here is if I'm trying to find dy dx at that point, we would write like 2, -1. That just means we're going to find the slope at that point, right? So I'm writing my dy dx over here, but I'm going to replace my variables with those numbers. Right, so everywhere I saw an x, I'm going to replace it with a 2. Everywhere I saw a y, I replace it with -1. That. And then we do all this math, and we get On the top, we will get basically 12 plus 4, right? This is 12 and this is 4. It's going to give us 16. On the bottom, we're going to get 4 times 1 times negative 9, which is 4 times negative 9, negative 36. 4 minus 36 is negative 32. And this is going to simplify to negative 1/2, right? So the equation of our tangent line is going to be y minus negative 1, which turns into plus, equals negative 1/2 x minus 2, right? We just use this equation, and for the m, we plugged in our little slope thing there. All right, so that's how that one goes. For part 2, you will not have 3 questions here. You only have 1, but I just wanted to show you the different types that are on there. All right, so you remember you'll have like 1 of these types, and you'll need to know how to do that type, but I'm going to do all 3 for you so you can see them. We're just trying to find dy dx in terms of x and y, so it's just basically, can I find the derivative implicitly, right? So let's do this. We're going to go ahead and take d dx of this whole thing, right? We're going to take the derivative of this whole thing with respect to x. Here, we're going to use power rule, 12y squared dy dx, right? So bring down this, multiply there, you get 3, subtract 1, you get 2, and then dy dx is the derivative of the inside. Oh my goodness, what a mistake. All right, don't do that, that's wrong. Right, notice how before I can even get into that, there's this exponent on the outside. That means this one has like an outside product and chain rule thing here going on. So first I need to take the derivative of this thing, which is going to be 2 of that thing to the first power times the derivative of that thing. So it's going to be 2 4y to the third plus 5x to the third raised to the first power times the derivative of the inside, which is now this 12y squared dx dy plus 15x squared, technically dx dx, but again that's just 1, and this is going to equal 1, right? The derivative of x is just 1. All right, I'm going to erase this little 1 because it looks like a prime, but it was just an exponent of 1. And here we are with this. Our goal, remember, is to find dy dx, right? So here's dy dx, my goodness, dy dx. So I need to get it by itself somehow, right? Right now it's in these parentheses, so I need to get rid of these parentheses first. All right, let's do this first. Let's go and distribute this 2 to give us this. All right, just to make this next step a little bit easier. All right, so we have that. Now, what we're going to basically do is we're going to take this whole thing and we're going to distribute it in there. All right, that is one way to do it. The other way would be just like FOIL it or something, but if I do it this way, it's going to save us a little bit of time. So if this is too confusing, you can just FOIL this and then take like other steps to get to the answer, okay? But it's basically going to be this whole thing times that, so it's going to be 8y to the third plus 5x cubed times 12y squared dy dx, and then that's going to be added to 8y to the third plus 5x cubed times 15x squared. This equals 1. And the reason we did that is now this term over here is the only one that has dy dx, so I can kind of solve for it, right? So the idea is I now want to move this whole term to the other side, right? So we're going to do that. It's going to become, this piece is not going to change any. This is going to be over there, so it's going to be 1 minus this 8y cubed plus 5x cubed times 15x squared. And then the last thing I have to do is I'm trying to get this by itself, so basically we're going to divide both sides by this, right? I don't know why I'm putting parentheses this time when I didn't do it the other way, but it doesn't matter. Right, we're basically dividing both sides by that so that these will all cancel, and we will be left with dy dx equals this. And thankfully we don't have to like plug anything into this one, but that is what that answer should look like. All right. Oh shoot, this is supposed to be a trig one, so let's skip number 3 for now. Let's look at number 4. Number 4, again, we're just trying to take the derivative, right? So we're going to find the derivative with respect to x of this whole thing. We start with this, the derivative of e. If you remember, the derivative of e to the u is e to the u times u prime. So it's just going to be e to the 3y squared times the derivative of the exponent, which is going to be 6y dy dx. This is going to equal 8x plus 6x squared, and then that's gone, right? And again, the goal is to solve for dy dx. So basically we're going to divide both sides by e to the 3y squared power times 6y, right? We're dividing everything by that, and these cancel on this side, and we have this and then the other side, you know, we could try to simplify, but there's not really anything that simplifies over there. So we're just left with that. All right, and then let me get one other example that's supported. Okay, so I just went and pasted a different one in here, and this is more like what you would see for the trig one. Okay, so again, you only get one of these types, but you need to know how to do all of the types. Okay, so basically we're given that, and we want to find the derivative. So we're going to take the derivative with respect to x of it. So the derivative of x with respect to x is just 1. The derivative of 3x squared with respect to x is 6x, and the derivative of 2 is just 0. And then we're taking the derivative of the right-hand side. This requires you to remember what the derivative of cosecant is, which the derivative of cosecant is cosecant times cotangent times the derivative of the inside, right? So here's we're going to write right here. We're going to write the derivative of the inside, which is 3y squared dy dx. Right, and the whole goal, remember, is to solve for this guy. So basically we're just going to divide both sides by anything that's not that guy, right? We're going to divide both sides by that, and same thing on this side. And this whole thing here will cancel, right? So we'll just be left with dy dx equals 1 plus 6x over cosecant y to the third cotangent y to the third times 3y squared, right? And that is the derivative of that, right? So recognize, please, that this will not always be cosecant, right? Sometimes you'll have a cosine, sometimes you'll have a sine, sometimes you'll have a tangent, sometimes you'll have a secant, right? So you do need to remember all these ones, and, you know, obviously cotangent as well. You need to remember how to do those derivatives so you can apply it onto this one as well. All right, I hope this is helpful, and good luck when you take it.